Right. So this is being recorded as well. So we'll observe the normal protocols, right? So if you have any questions, you just unmute and you can ask a question. All right. I'll usually prompt for questions, but if you don't hear me, you can go ahead and ask your questions. So we are looking today at the rest of session 5, right, where we are going to start off by looking at the angle properties of circles, right? I'm just going to recall the 9 angle properties, but I'm going to focus on 4 of them that are most common and would be the more challenging ones to understand, right? So we have the first theorem on the right here, which is theorem 1, right? It says that the angle at the center of a circle is twice any angle at the circumference standing on the same arc, right? So if you have an arc here and you go to the center, come back, or from A, go to the circumference and come back, there's a relationship between the angle at the center and the angle at the circumference. And it is that one is twice the other one. So the one at the center is twice the one at the circumference. And that is a very basic theorem. We have it as theorem 1 here, but it could be in somebody else's notes, theorem 3. All right, so just in our looking at it, this is theorem 1. Okay, so right now, I have written on this side here, right, on the left side, the theorems that we're going to look at in a shortened version, right? And it's good to have all of 9 of them there so that you could always very quickly review them, and you should have it somewhere on a card or notebook or whatnot, right? So the angle, this symbol means angle, right? So angle at the center is twice angle at the circumference, right? And there are different versions of this. Center is twice circumference, center is twice circumference, standing on the arc AB. All right, the next one, right, that we look at is number 2. So let's go down to number 2. Right, theorem 2, the angle in a semicircle is a right angle. So we have it here, angle in a semicircle is a right angle, mean is equal to 90 degrees. So if you look here, you see that there's a semicircle because AC is a diameter and it forms a semicircle, right? Where on one side is a semicircle, on the other side of the diameter is another semicircle. And if you go from one end A to the circumference and come back, you form a 90 degree right in the point there where you meet on the circumference of the circle. Similarly here, A to B to C, you create a 90 degree here as well. So you have to realize that the angle in a semicircle is a 90 degree, and this is our abbreviated form. This is our abbreviated form here. Theorem 2, therefore, is angle in a semicircle is 90 degree. The third one now, let's look at the third one. That will be theorem 3. It says that angles at the circumference of a circle standing on the same arc are equal, or in a more abbreviated format, angles in the same segment of a circle are equal. So once the angle is being formed in the same segment, they will be equal. So if I have this chord here, AB, and it's cutting the circle into 2 segments, the minor segment below, which is the smaller one, and the major segment above the chord, right? If you go to any point on the circumference, let's say D, and come back to B, we'll form an angle X. And if you go from A to C and come back to B, you form another angle X as well, right? Because these angles would be the same. Why? Because they are in the circumference, but in the same segment, right? So we say across here in an abbreviated format, angles in the same segment are equal, right? So even if you look here, this chord AB, right? Down here is the minor segment and above here is the major segment. This is one segment here, this is another segment here. And once you go to that segment, circumference, come back to B, and in the same segment, go to D and come back to B. The angles formed at the circumference there, they will always be equal, right? So you're supposed to be aware of this and look at the little slight examples and be able to deal with them. They're very easy examples, so you should be able to handle those quite easily, but you're supposed to know the theorems. The fourth theorem, which is theorem 4, right? Let's look at it. The opposite angles of a cyclic quadrilateral are supplementary. Now, supplementary means when you add up those angles, you get 180 degrees. So basically, the opposite angles of a cyclic quadrilateral are or add up to 180. So look, we have it here in our summary here. Opposite angles of a cyclic quadrilateral sum to 180, right? I try to make all of these in one line. Opposite angles of a cyclic quadrilateral sum to 180. Now, firstly, what's a cyclic quadrilateral? Well, a cyclic quadrilateral is any four-sided shape whose vertices are enclosed in a circle such that the vertices touch the circumference of the circle. For example, this one here and this one here, both of them are cyclic quadrilaterals. Now, opposite angles will be B and D, for example. And the rule or the theorem says that if we add B and D together, we're going to get 180. If we add A and C together, we get 180. Similarly, this one here, cyclic quadrilateral, because A, B, C, and D are all on the circumference of the circle, and the circle goes around it like this, then A and C added together will give us 180, and B and D added together will give us 180 because of theorem 4, which is this theorem here. In theorem 5 now, this is where we're going to start to look at the actual questions, right? Some examples, because they would be a little more involved, right? Let's see where that is. That will be, right? This is theorem 5. It says that the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle, right? The exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. So let's look across here now, right? The exterior angle of a cyclic quadrilateral is equal to the interior, int, opposite angle, right? So again, we're trying to make it as small as possible so we could, we could grasp it and hold it a lot easier. Now, what does this mean? The exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. All right, so let's look down here now. Right, I'm going to enlarge it so we could see it better, right? And in this cyclic quadrilateral here, there are 4 interior angles, B, C, D, and E, right? Outside here, this one here is an exterior angle. This one is exterior. This one here is exterior. This one is exterior. And what the theorem says is that the exterior angle, let's say this one here, is equal to the interior opposite. So that if this is B, this will also be B as well. If this is B, this will be B. Let's check another one. The exterior angle here, which is C, is not equal to the interior next to it, is equal to the interior opposite, or opposite angle to the interior, which is this one. So C is going to be here, the value here, and C is going to be the value here. Let's do one more. Let's look at this one here. This is the exterior angle because it's outside of the cyclic quadrilateral. So there's an exterior angle. And let's say that angle is A, then the exterior angle is not equal to the interior, it's equal to the interior opposite, or the opposite of the interior angle next to it. So this angle is not equal to this, it's equal to the opposite to this interior angle, which is this one here, right? The exterior angle is equal to the interior opposite. So this angle here will also be A if this one is A. And so the same applies in this triangle, in this quadrilateral as well, the cyclic quadrilateral. Take, for example, this exterior angle is not equal to the interior one here, is equal to the interior opposite, which is this one here. Okay, so that is theorem 5. But we want to look at the example that is associated with it, because as I said, this will be a slightly more challenging theorem, right, than the others. So let's quickly look at them, right? And in this particular question, it said without measuring, find the magnitude of the unknown angles in the circle, stating reasons for your answers. So if we look at this here, the unknown angles will be S and Q, right? Now we could solve this in more than one way, because as you know more and more theorems, you'll be able to apply those theorems and you'll be able to solve, many questions in different ways. So the method I'm going to show you is not the only way, but it's a way that we will use if we want to use the theorem that we just learned, right? Which was theorem 5, that said that the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. So right here, if you notice, there's an exterior angle here, and that's equal not to the interior, but the interior opposite. So angle Q must be equal to 85. So we write it here, angle Q must be equal to 85 degrees. And that is because of our theorem 5. What is our theorem 5? The exterior angle is equal to the interior opposite angle. So another important lesson here, or point, is that when we state a fact using a theorem, we must write back that theorem. We can't write T5 like I did here, right? I wrote T5 to remind you that it's our theorem 5. But what we would have to do is actually write it in either long form or shortened form. This is an acceptable shortened form because this here would represent angles and this here would be abbreviated words. So exterior angle is equal to interior opposite angle. All right. And therefore we were able to find this unknown angle Q. The other angle we needed to find was angle S. So what we said is we would apply theorem 4. Theorem 4 says that the opposite angles of a cyclic quadrilateral sum to 180 degrees, which is what we wrote here, but in a very shortened form. We wrote opposite angles are supplementary, right? That means that in this cyclic quadrilateral, the opposite angles add up to 180 degrees. So that's what we wrote here. S plus Q must be equal to 180. S plus Q, they are opposite angles in the cyclic quadrilateral, right? RQPS is a cyclic quadrilateral, and these are the opposite angles. So if we add them, we must get 180 according to theorem 4. And we already got angle Q up here as 85. So we just put 85 here. S is unknown. When you add them, you get 180 from this theorem. And so we just solve the equation. So S would be 180 take away 85, which is 95 degrees. So in that way, we were able to use two theorems mainly, right, to get our answer. Right, and there are other ways to do it, and very obvious to get this one. If we didn't know that theorem, we could easily say that angle S plus 85 is 180, and therefore subtract 85 from 180 and we get angle S. The theorem there is that the angles are on a straight line and they would add up to 180. And then we could use theorem 4 here, right, to get what angle S is. We could get angle Q by using theorem 4, which says that when we add them together, they must be 180. So those are two ways that we could solve this particular question. And, you just be aware that when you're solving, you choose the method that would be easiest to you and use the theorems that come easiest to you. All right, so that would be that particular one. The next one we're going to go to is theorem 6. And theorem 6 says that the radius of a circle drawn to the point of contact of a tangent is perpendicular to the tangent. All right. So again, we could shorten this and make it into a nice form. And when I go back to the other version of this page, you will see it shortened, right? But for now, we will just use it as it is. So basically what it's saying is that the radius and tangent, where they meet, which is right here at T, you'll always have a 90-degree being formed. But if 90 is on one side, 90 will be on the other side as well, because it's a straight line. Okay, so you must always remember that. And in this particular question, right, if we look down at this diagram here, this reflects the information given. Not this one here, this is the answer, right? So you're really going to start here. So let's look at this example where we're going to apply theorem 6, right? So in theorem 6, we're going to use theorem 6 here. Let's see why. TA is a tangent to a circle. So if we look here, TA would be that tangent. And ONT is a straight line. So ONT, this is a straight line. Good? Given that OTA is 24 degrees, OTA is 24 degrees. That's how we get 24 degrees. So they may not have written it in for you in your exam. So you have to be able to pick up that the angle OTA is 24 degrees by tracing the part OTA and recognizing that that is where the angle will be. That's 24 degrees. They want us to calculate these angles here, OAN and ONA, right? But if you notice in the original diagram, they did not show you where OAN is or where ONA is. So you have to be able to decipher where these angles would be. Okay, so let's locate OAN first. So we start at O and we're gonna go down to A, right? So we're going this way, and then we're gonna go from A to N. So you notice there's no line carrying you back to N, so we're gonna draw that down, right? So we're gonna go to O. That's now, let me go back and put in my pen. So we're going to O to A, and then we're going to go across to N, right? So with that's the angle we want to get here. I'm going to draw it in here, this angle here. That will be the angle that they want, which is OAN, right? They also want the angle ONE, right? There's this angle here, ONE. So where's ONE? Well, if we start at O, we go down to N, and we come back across to A, then the angle so formed will be this angle here, and that will be the angle ONE. Good? So now that you know the angles that you want, you could proceed and try to solve it. All right? So let's first try to solve for OAN. OAN, right? And we know where OAN is, this one here. All right? Now, what we can do firstly is locate this angle here, which is AON. That's the one right up at the top here, right? And if we get that angle, we could solve OAN and ONA angles by using the properties of an isosceles triangle. I'll show you that shortly, but let's work out, let's see how we could get that angle up there, this one up here, right? Which is angle AON, by the way, AON, right? Let's see how we can get that angle. Okay, well, I'm going to look at the triangle OAT, right? That's OAT, that triangle I'm going to look at. And I recognize that OA is a radius and AT is a tangent. And if you recall, theorem 6 says that the radius and the tangent to a circle, they meet at 90 degrees. So OA and AT are going to meet at a 90-degree angle, right? So let's see if we could get this in color to change to red and show that 90-degree angle right there. So that 90-degree will be at this location where I'm putting in the red mark, right? Because of theorem 6. So theorem 6 tells us that this here is going to be, that's theorem 6, a right angle. What is it again? Theorem 6 says that the radius and a tangent to a circle are going to meet at 90 degrees. At that point where they meet, that point of contact, which is A in this diagram, is going to be 90 degrees. So if we look at the triangle OAT, and we notice that we have one angle at the bottom there by A, that's 90 degrees. We have one angle by T, which is 24 degrees. But the angle on the top, right, which is this angle here, AON, we could work that out by recognizing that if we add up the three angles in the triangle OAT, we must get 180 degrees. So to get the angle AON, all we're going to do is say 180, take away 90 and 24 at the bottom. So let's take away 90 plus 24, okay? And that is going to give us the angle AON. So let's see what we get for that angle when we work it out. Just 1 second. I'm trying to get back to my document here. Right. So that angle works out to be 66 degrees. When we do that calculation, this angle up here is going to work out to be 66 degrees. Okay. Now, how can that help us to find these two, OAN and ONE? Well, let's look at something. From O to A is a radius, right? That means that OA is a radius. From O to N is also a radius because it's from the circle center to the circumference. So it means that we have two equal sides, which I just put in with double with double red lines. Okay. So if we shift up to the diagram up here, because it is not looking as convoluted as the one below, right? You could see that I have put in one O to A as R and O to N as R also, right? Two radius. Now, if both of them are the same length, both of them are radiuses, then the triangle OAN is an isosceles triangle. OAN is an isosceles triangle. The angle at the top here, AO, and that angle at the top, that is the apex angle, and we know that is 66 degrees. And the other two angles would be base angles, which means that this angle and this angle, both of them are base angles in the isosceles triangle, OAN, and they will be equal in magnitude. Okay, so whatever I get for the angle OAN, it'll be the same value for angle ONA, because in an isosceles triangle, right, where the two equal sides meet will be the apex angle, which is this one up here. And the other two, which I just pointed out to you, OAN and ONA, are the base angles. And they will be equal. And let's say they were equal to theta. Then what we are saying is if we add up OAN, which is theta, and we add up ONA, which is theta as well, that'll give us 2 theta, plus we add up the 66. We know that all three of them must work out to be 180 when you add it up, because angles in a triangle sum to 180. So if we write down 2 theta plus 66, we must get 180, because angles in a triangle sum to 180. That means that 2 theta will be equal to 180, take away 66, by bringing the 66 on the other side and changing the sign, or simply minus 36 on both sides. And then if we divide the left-hand side by 2, we'll get theta. That means we must divide the right-hand side by 2 also. So it means that we'll get a value for theta, and that works out to be a value of 57 degrees. So what that is saying is that the angle OAN is equal to 57 degrees. So that'll be the answer to this first one. And it also means that the angle ONA is also equal to 57 degrees, because they are equal. Okay, so I took my time and went through it in detail, because this would be a more involved question to what you would normally see. All right, so let's go to the next one. Right, so that was theorem 6. We're going to go to theorem 7. Right, now in theorem 7, let's read what they say. That tangents to a circle from an external point T are equal in length. So basically, if we go from T to A, right, that is a tangent, and it's coming from this external point T, right? I think it should be a common external point T. Right, let's put common, because both of them are coming from that common external point T, right? And if we go from T to B, right, what we realize is that according to this theorem, those two sides would be equal, right? So that's theorem 7, and we take note of that in our shortened form as well. When I come back to that screen, I will show you that shortened form. So we come back, so we come and look at a potential question here, where they say tangents to a circle. TA and TB are tangents to the circle. So I'm reading the example question. TA and TB are tangents to the circle center O. AB is a chord So let's see AB on the diagram. A to B, that line is a chord. Calculate AOT and TAB. So in order to calculate it, we have to know where AOT is. So AOT is this angle down here that I just highlighted. That is the angle AOT. Right? TAB, angle TAB, where is that? TAB, that's this angle here. Angle TAB. So those are the two angles we have to find. So that's what you have to do firstly. When they tell you a problem, you have to identify what the angles are. Now, our strategy for finding angle AOT will be to find the angle AOB firstly, which is this one I'm drawing here. That angle that I just drew in there, that is angle AOB. I'll find that first. And there's a bit of knowledge you need to know, which is that if you have a kite and you are able to find that angle, then the line OT bisects that angle, cuts it in half, so that you can get the angle AOT, which will be half of the angle AOB, right? So our job to get angle AOT will firstly be to calculate angle AOB. So if you notice here, I have in part A, we're going to find angle AOB first. Now, how are we going to go about finding angle AOB? Well, let us look at the kite TAOB. There's a kite in this drawing. The kite is, follow me, T to A to O to B, and back to T. So I'm going to draw some arrows so you'll see it, right? You're going from A to T to A, then A to O to B, B back to T. So that creates a kite. Now, if we look at the angle by T, that angle there is 56, right? If we could get this angle up here, this angle here, right? And angle AOB, and add them up together, we must get 360 degrees. How do I know that? Well, you guys are supposed to know that in a triangle, the sum of the interior angles is 180. In a quadrilateral, any quadrilateral, it's 360. And in any pentagon, it's 540. And then there's a formula that Rena had told us about the last time that we could use for any n-sided polygon. So if you weren't here, you could go back on our YouTube channel and you can see the, the video on what we did last, where we spoke about that formula. So we are going to use the fact that when you add up all the angles in a quadrilateral, a kite in this case, you get 360. So in this kite, TAOB, if I add up those angles, I'll get 360. But the angle up by A, which I'm going to highlight now, this angle here, I'm highlighting now with two arrows there, that angle I will say is 90 degrees because of theorem 6. What does theorem 6 say again? Theorem 6 says that the radius and the tangent to a circle meet at 90 degrees. So the radius OA and the tangent TA, they meet at A and they create a 90-degree relationship. So there's a 90 degree here, right? The same thing is going to happen at B because the radius OB meets the tangent TB. And according to theorem 6, there's a 90-degree relationship between the two. So we basically found the angles that we needed, right? So let's add up the angles. The one down here in the kite is 56 degrees. The one up by A in the kite is 90 degrees, right? The one down by B is 90 degrees. And then the only other angle in that kite will be the one up at O, which will be the angle AOB, which is this whole angle, right? This whole angle here. All right, so let's write it in AOB. And all of that is going to equal to 180 degrees, right? All of that is going to be equal to 180, not 180, sorry, 360, because it's a quadrilateral, right? So basically, we could work out what AOB is by adding up the 50, 60, 90, the 90, and using that in our formula. So let's add up that and see what we get. So 90 and 90 is 180, right? And we're going to add up very quickly the 180, right, plus the 56, and we're going to get 236. So if we add up all of these things here, we're going to get 236 degrees. So all we have to do is say 360, take away 236, and that's going to give us angle AOB. Simple algebra. And of course, if I do that calculation, 360, take away 236, I'm going to get 124 degrees. Okay, so what that is saying to us is that the angle AOB is 124 degrees. But we don't want angle AOB. The question for A is angle AOT. So we know that AOT is half of AOB because that's the property I spoke to you about earlier with a kite. So I'm going to take the AOB that I got as 124 and put it up here for AOB. And I'm going to divide that by 2. And that's going to give me angle AOT. Right? 124 divided by 2 is 62 degrees. So we found angle AOT to be 62 degrees. So angle AOT worked out to be 62 degrees. The next thing we have to work out is angle TAB. TAB. So look where angle TAB is up there. Right? I'm just trying to change the ink color a little bit. Let's go with blue. Right? So look at angle TAB. That's what we want to get up here. That's this angle right here. So firstly, I'm going to mention to you that the length AT, is equal to the length TB. AT is going to be equal to TB. Why am I saying that? Because of theorem 7. What is theorem 7 again? It says that tangents to a circle from a common external point are equal in length. Right? Tangents to a circle from, which is theorem 7, tangents to a circle from a common external point are equal in length. So that's why I could say that TA must be equal to TB. So that's why we wrote this here. TAT equal to TB or TA equal to TB. And that's theorem 7. So now, if I look at the triangle TAB, right, I have a triangle looking something like this. TAB, right? I can find that triangle, I can deduce that that triangle is an isosceles triangle. So why is it isosceles? Because in any triangle where the two sides are equal in length, that's isosceles. Where the two sides meet, which is right here, that is going to be the apex, right? And that apex is going to be 56 degrees. Good? The other two angles, this one and this one here, those would be the base angles and they would be equal. So we could easily find that. We could find this angle and this angle. Let's call them theta. Make it easy for us. We could say that if we need to get either of those two angles, we just take the 56 away from the 180, which we know all three of them will add up to, and divide the answer by 2, and we'll get what either one of those two angles are. So we could say that theta is going to work out to be 180, take away 56, divide the answer by 2. And that'll give us what any one of those two are, right? Because they are two equal angles. And if we do that, we will get theta to work out to be 62, I believe. Yeah, theta's work out to be 62 degrees, which means that either of those two angles there will be 62 degrees. And we know the one up at the top here is the angle TAB. TAB, right? That's the angle TAB that we're interested in. So we would have gotten our answer for TAB to be 62 degrees. All right, so we were able to go through and get those answers. As you will, I'm sure you agree, these are the more involved ones, so it does take a bit of, working. The next one we're going to look at will be the last example of theorems that we will look at. There's one more theorem. I would not do the example, but I'll just bring your attention to it when I flick back to the original screen. But before we go there, we're going to look at theorem 8. And what does theorem 8 says? Is a kind of lengthy one. It says that the angle between a tangent to a circle and a chord, right? Let's identify that angle firstly. The angle between a tangent to a circle and a chord. So let me just change back my ink color to red. Right, so make it easier to see it on the black. So the angle between a tangent to a circle and a chord. So let's look at the tangent TA, for example, and let's look at the chord AB. There's an angle between those two, and that's this angle here. Right? This angle is angle X. So the angle between the tangent and the chord at the point of contact is equal, in this case is X, is equal to the angle in the alternate segment of the circle. So what alternate segment? Well, okay, if we look at the chord AB, so I'm just highlighting that. The segment where we located X between the chord and the tangent, T, right? That segment is this one that I'm highlighting here, right? So there's an alternate segment to the one that X is in. That will be the one at the top. That'll be the segment up here, the other part of the circle on the other side of the chord AB. That's the alternate segment. So the angle formed between the tangent TA and the chord XB, right, at the point of contact, which is X, is equal to the angle formed in the alternate segment, which is this one here, formed by that same chord, right, at the circumference. So a good addition to this, right, should be at the circumference, right? So at the circumference, meaning by the same chord AB, we're going to go to any point on the circumference in the alternate segment and come back to A. Then you're going to form the same angle here, right, at the circumference. That will be angle X. And you could look at it from this point of view here too, because there's a tangent TB to the same chord AB forming the angle between the two of them, right? Still in a segment below, this segment below, right? And if you extend that same logic by going from AB to this point here, let's call this point C, right? You'll find that that angle will also be working out to be X based on theorem 8. So it is a mouthful, but let's say it again. The angle between a tangent to a circle, let's say for example TA, and a chord AB at the point of contact, which will be the angle X, is equal to the angle in the alternate segment of the circle, which is the segment on the left-hand side, but we put in something that will help us at the circumference, right? At the circumference formed by that same chord AB. So that will also be X at this point, okay? So that's what that theorem is about. Let's see if there's anything that we could look at to see how we could utilize it, right? And we're going to utilize it here. It says that in this case, in this case, ATB is a tangent to a circle, right? So we see in A, we see in T, we see in B, right? That line there is a tangent to a circle, right, at T. And CT is a chord. Let's draw in CT in red so we can see CT, right? That's a chord. So we could look at some properties there. If TDC is 35, okay, where's TDC? TDC is 35. So this here is TDC. That's 35. TCE angle is 65. TCE, that's this one here. TCE, that's 65. Estimate, firstly, the angle A, right? We want to find out where angle TEC is. Okay, so let's look for TEC. TEC means go from T, go to E, right? So we're going like this, and then we go into C, which means we're going down like this. So the angle TEC, which is the first one, will be this one here. That's the angle they're looking for, TEC. Now the theorem we're going to use to find TEC is theorem 3. Even though we have to use, in this example, we are supposed to be using theorem 8. What this shows you is that as you get more advanced in these topics, when you see a question, there may be 3 theorems, 4 theorems, 2 theorems that you have to pull on to get the answer, right? The answers. So here, you have to get an answer for TEC. And the theorem we had to use here is theorem 3. What is theorem 3 again? It says that the angles in the same segment of a circle are equal. Okay, so let's see what that means. If we consider the chord TC, so I'm drawing it back again. If we consider that chord, and we go to the circumference in this top segment, so we're going from T to D, and then we're coming back down to C, right? We forming an angle in the segment, the top segment, and that angle is 35 degrees. That's this angle here. If we go from that same chord TC to another point E in that top segment and go back now down to C, right? You're going to form another angle in the same segment, TEC, and that TEC must be equal to the angle TDC, which is 35 degrees. How come? Because those angles are in the same segment of the circle. So based on theorem 3, the angle TEC must also be equal to 35 degrees. So that's that first one. The second one we had to do was angle CTB. Okay, so where's CTB? Well, let's start at C. Let's go to T. And let's go to B. So we creating this angle here, which is the angle CTB. So you have to work out the angles they want. All right, we're going to use theorem 7 to solve angle CTB. What is theorem 7? The tangents to a circle, right, from a common external point are equal in length. No, that is not the one we're going to use. That's the wrong one. We're going to use theorem 8. So this shouldn't be theorem 7. It should be theorem 8 because there are no tangents from a common external point. Let's look at theorem 8 instead. The angle between a tangent and a chord at the point of contact is equal to the angle in the alternate segment of the circle at the circumference. Okay. All right. So let's see what that is about. So the angle CTB between the tangent ATB and TC, that angle is equal to the angle in the alternate segment, right, formed by that same chord TC at the circumference. So not in this segment down here, but in the segment on top there. So this angle up here must be equal to this angle down here, right? And that is because of theorem 8. The angle between the tangent ATB and TC, the chord, must be equal to the angle in the alternate segment, which will be the one at the top, right? Formed by that same chord TC at the circumference in the alternate segment. So if TEC is 35, then CTB must also be equal to 35 degrees according to theorem 8. So we're supposed to get 35 degrees here as well. Okay, the last one is ETA. So where's ETA? You go from E, you go down to T, and then you go across to A, right? Go across to A. So we're going to form this angle here, and that will be the angle ETA. How do we find that angle? Well, we're going to use theorem 8 again, not theorem 7, theorem 8. What does theorem 8 says? It says that the angle between the tangent ATB and the chord ET which is the angle ETA that we just showed here, right? That angle is going to be equal to the angle formed by the same chord ET at C in the alternate segments. Not the segment where ETA is, not on that side, but on the other side, formed by the same chord ET, but at the circumference. That will be this angle here, the 65 degrees. So that angle 65 degrees, which is the angle TCE, it must be equal to angle ETA. It must be equal to that angle there because it's been formed at the circumference in the alternate segment. It's been formed by the same chord ET that ETA is formed with on the other side. So ETA must be equal to 65 degrees according to theorem 8. So that's 65 degrees. All right, so those were the main examples of these theorems that I wanted to go through with you because they are pretty important. All right, there's another theorem, right, that deals with, that's theorem 9, right? It's just worth mentioning. I don't really see it in exams, but it's worth mentioning. And it basically says that if Tx is a tangent, where's Tx? Tx is the tangent, that's here. And AB is a secant. Secant means it comes out of the circle. So it should really be ABX, right? But it comes out of the circle. So up to here, that's a chord. But as it comes out and it goes out, that it becomes a secant. And it meets the tangent at Tx, at X, Tx at X. Okay, so there's a meeting there. What they say, there's a mathematical formula that says that Tx squared, the length of the tangent squared, is equal to AX, which is the total length of the secant, times XB, which is the external part of the secant. When you this dot here means to multiply. Okay, and you can use that accordingly, but it's something very, very rare, but it's on your syllabus to learn that theorem. Okay, so if you recall, I had all the angle properties of a circle. I told you we'd abbreviate it. So it's all there. And you could always look back at the video that I will put up on YouTube. And you will be able to get back all the shortened versions. So it's good that you learn them. Don't worry with this here. This was just my notes of which slide it was. So don't worry about that. Worry about everything that is in red and learn it so that you will be able to apply it. Remember that when you use these theorems, you're supposed to be able to tell them what theorem you're using at various points. I use abbreviations. I put T5 and T4 and so on. You wouldn't have that luxury. You would have to say the theorem using is the angle at the center is twice the angle at the circumference, for example. Or the angle in a semicircle is 90 degrees. You have to write it out. You could write it out longhand or you could write it out shorthand. It doesn't matter. Anywhere you feel comfortable. Okay? So that would be our theorems as it relates to circles. But what we'll be going to next will be our statistics, right? The next thing we're going to be looking at is statistics, right? And you guys might remember what statistics are about, right? And we're going to go through it fairly quickly. Not going to spend too much time, but we're going to go through it thoroughly. And these are the easier parts of statistics we're looking at today. What is statistics again? It is the name given to the science of collecting large quantities of facts or data and studying or analyzing them. All right. And the first statistics that we normally look at, the first chart that we normally look at is the proportionate bar chart or the composite bar chart. And these bar charts or composite charts are normally a single rectangular bar, which could be drawn vertically or horizontally. The rectangular bar is subdivided into different heights or lengths in order to represent the various magnitudes of data, right? That is a very important one. It's very easy, but you could get it, and it's quite easy. Now, the table below shows the ways in which a certain country spent its budget for a particular year. If you have to show this using a proportional bar chart, right, it's quite easy. Here they tell you the wages 33 million, health 24, education 15, agriculture 13, and communication 5. And if you have to show this on a proportionate bar chart, it's quite easy. What you would do first is to select an appropriate width, right? Anything that is convenient to you to put on your page, you can select that. So I selected 6 centimeters for the width. The heights are what is important. So what we do is we would add up, right, from the chart all the amount spent in the different areas. So we would go back here and add up wages and salaries, health, education, agriculture, and communication, add these up, and that would tell us the total amount of money we have to show on our bar chart. So if you add up these numbers, you're going to get 90 million. So our bar chart has to show $90 million, right? Our proportionate bar chart. So you have to decide what scale to use to show that. Now, if we use this scale here, 1 millimeter to $1 million, it means that to show $90 million, which will be the total height of our eventual bar chart, using this scale, it will be 90 millimeters for $90 million, right? Because when we added up all of these, we got 90 million. So to show all of it, we know that using this scale, 90 million would be 90 millimeters. And 90 millimeters is really like 9 centimeters. And if you take your ruler and you check it on your page, it could comfortably fit on a standard page that you would have in an exam, or your copybook page or binder sheet. So that's convenient, and it will work well. So we're going to use this scale here to come up with our proportional bar chart. So you would have started off by just by drawing this line here, and you'd have to figure out what height to make this based on our scale of 1 millimeter to $1 million by looking at what wages was. So if you go here, wages was 33 million. So if the scale is 1 millimeter to 1 million, obviously 33 would be 33 millimeters to represent 33 million. So that means that for this part here, right, we would have to write, we'd have to not write, but measure 33 millimeters. So we draw a line up 33 millimeters on the right. Then we draw a line up as well, 33 millimeters on the left. And then once we do that, we're going to draw a line across. Bam. And that will give you wages and salaries. Then you'd have to consider the same thing for health, right? Which would mean that you'd have to go back to your health, see how much it was, 24, right? It was 24 million here. And that means now that the height here now would have to be 24 millimeters. Why? Because the scale that we choose to allow everything to fit was 1 millimeter to $1 million. So if this is 24 for health, it means that this here has to be 24 millimeters. So again, we would have to measure 24 on the right, measure 24 on the left, and we would be able to come across, right? And we will get our health bar. Then education was 15. So that means here had to be 15. This side had to be 15. Draw across. That would have given us education. Then health 24. Sorry, agriculture 13. So we'd measure here 13. On the other side 13 as well. And draw across horizontally with our ruler, right? And you would get agriculture. And the last one, communication, was 5, right? Communication was 5 million. So that means that the height had to be 5 millimeters on the right. And we'd also measure 5 millimeters on the left. And then we draw a horizontal line across. And of course, at that point, we would have our proportional bar chart. All right, so it's one of the simplest ones to draw, the simpler ones to draw. And besides our proportionate bar charts, the next one in line would be our basic bar charts or column graphs. Now, these are very similar to what we would meet in the future in terms of histograms. But these charts have, these bar charts are, or column graphs are very easy. They really consist, right, of a number of rectangular bars of the same width, right, which can be drawn vertically or horizontally, right? The one that we are going to draw are vertically drawn ones. And these are evenly spaced out. These bars are evenly spaced out. So they are rectangular bars, same width. We are going to draw them vertically and they'll be evenly spaced out. Right? Now the height or length of the bar is directly proportional to the magnitude of the data it is representing. So let's see what that means. If we had a situation here where in this table, we were showing the heights of the principal waterfalls in South America. On the left-hand column, you're seeing all the names of the waterfalls. For example, the first one is called the Angel Waterfall. Its location is in Venezuela, and its height is 979 meters. So basically, all of these waterfalls, they wanted us to draw a bar chart, which is also called a column graph, to represent the recorded data. All right? So how do we go about doing that? Well, we have to come up with a scale. So we came up with this scale here, 2 centimeters to 100, but that should be 2 centimeters to 100 meters, not centimeters, but meters. So let's fix that. I just want to change, let's just change it here. Right, 2 centimeters to 100 meters. And that means that if I check here, that's 1 centimeter, that's 2 centimeters. So 2 centimeters to 100 meters. Or if you wanted, you could write 1 centimeter to 50 meters, and that will be your scale on your y-axis. On the x-axis, all we do is we separate the bars evenly, right? Even spacing in between each bar, and each bar would have the same width. And then you just simply measure your height. So for example, the first one, the Angel, was 979. So we would have to show 979 right here. So this would be 979 here. The second one was 610. So you'd have to get 610 right on your scale. And that height would be this height right here. Okay, the next one would be 488. You'd measure that, get your height, draw up your bar. Next one, 404. Next one, 300. Next one, 256. Next one, 256 meters. And we would draw our height of our bars, right, to reflect all the information given in these columns here. All right? Once you do that, you would have drawn your proportionate bar chart. Fairly simple, but of course, practice makes perfect. Okay, the next one is the chronological bar charts, where it's very similar to the normal bar charts or column graph, except that time is now on the horizontal or the x-axis. Time is now along the horizontal, which is normally called the x-axis. So in this particular example here, they wanted us to construct a chronological bar chart to show the information given in the table for a 5-year period, right? So the 5 years will be 1989 to 1993. And there was some expenditure, right, for, I don't know if it's a business or, well, it would hardly be a country, but probably it's a business. And it was like in 1989, the expenditure was like 15 million. In 1990, 17 million, and so on, right? And we need to show a chronological bar chart to show this information, right? So it will look very similar to the one that we did before, except that time, right, is now, this axis here is time, right? And it shows the years. So 1989, 1990, 91, and so on down to 1993. Again, the bars have the same width and they are evenly spaced out, right? The scale on the y-axis, which is where we show expenditure, is 1 centimeter is representing $1 million. So each block, let's say from here to here, that block is 1 million. The other one is another million, so that'll be 2, 3, 4, 5, right? And then you could plot. So your first one was $15 million in 1989. So this is 15, this height here will be 15. The second one in 1990 was 17 million. third one 18 million, and so on. So your height would reflect the particular expenditure for that year. And so this is how you would draw your chronological bar charts. Very simple. Just the wording you have to get accustomed to. A very common one is the pie chart. And pie charts are circular diagrams, which is another way of illustrating statistical information. The circle is divided into sectors of varying sector angles or areas, and each sector angle or area is directly proportional to the magnitude of the information it is representing. Normally, in reality, if you're presenting it, you would shade each sector in a nice different color, bright color. Okay, so in this particular question, example here, we're looking at, they say the table below gives the number of graduates by subject from a teacher's training college in 1982. The first thing they want us to do is to calculate the total number of teachers that graduated. So if this is the chart that shows the number of teachers graduated in each subject, the total would be to add up all of these figures here, right? That would be 17, 25, 10, 15, and 23 added together. So our total was 90 teachers in all. Okay. The second question they asked was part B, determine the sector angle that will represent the number of teachers graduating in each subject area. Okay. Well, we know that there are 90 teachers in all. And for example, in mathematics, there were 17 teachers that graduated that year from our table. So if the whole circle was 360 degrees, then to get the angle that we would use to represent mathematics, then that angle will be 17 teachers that graduated in mathematics out of 90 teachers in all. That'll be the fraction of the circle that we have to allocate for mathematics. So it'll be 17/90ths of the total 360 degrees, and that worked out to be 68 degrees for mathematics. Then we would go to English. And if you notice, English had 25 teachers. So that'll be 25 over 90 by 360. 25 over 90 by 360. So that'll give us 100 degrees for English students. And then we would go and do that for each amount, right? So if we know physics is 10, it'll be 10 over 90 by 360. Chemistry is 15, 15 over 90 by 360. And history, 23 teachers graduated. So it'll be 23 over 90 by 360. And of course, that would give us the angles that we are interested in for history, chemistry, physics. Okay, now that would answer that part of the question. Let's go back again and see what is the other part. In part C now, they said, hence construct a pie chart of radius 2.2 to represent the information given in the table below. Okay, so not a problem. We already have all the angles, right? Mathematics was 68, right? English 100, and so on. So we will take note of the various angles that we have to represent, and then we would start to draw our pie chart. So the first thing we will do, if you look here, is to get the center of the circle, right? I'm going to put it in, I'm going to change my ink color to red, right? And I would get my center. If they said that they wanted the radius to be 2.2 centimeters, I would draw a horizontal line, 2.2 centimeters. And then I would take my compass, stick the point at the center, and draw the circle that you see drawn there in black, right? So that circle is drawn out. So then I would start to draw in a particular order. I would start with the smallest angle and then go to the largest angle. So my first measurement would be 40 degrees, right? And once I get my 40 degrees with my protractor, I would draw that line there. If this is 40 degrees here, and that would represent the first, the smallest angle, which was really physics, right? Physics graduates. Then I would look for the next larger angle. After 40, the next one above that would be 60 degrees, and that was chemistry. So I would then measure 60 degrees, and wherever that 60 degrees was, let's say that's 60, I would draw my line along that 60, and that would represent chem. Then the next one was maths at 68. So I would measure my maths, right? 68 degrees, and then draw, of course, draw the line, which is this line here, right? And that will represent maths. Then the next one after that was history, which was 92 degrees. I would draw my 92 degrees, which would bring me somewhere on this side here. So that would bring me to my history. Which is 92 degrees. All right, and that will be history. And then what would remain should be when you finish 100 degrees. So when you check here, you should get 100 degrees. And that would represent your last portion, which would be English. Okay, so in that way, you would come up with all your angles, all your sectors. And of course, if you could have color, you colored, but you know, in CXC, they don't allow you to color anything. But if you could have, it would have looked, you know, something like this, where everything would have been nicely shown based on a color code. Okay, and that is how you draw your pie chart. After the pie chart, there's something called line graphs, right? And a line graph is basically a graph that follows a line in a consecutive manner. So let's read it here. A line graph shows the data by means of drawing a line, as the name suggests. It is a graph constructed by joining a set of points together in a consecutive manner. The set of points represents known values of a given variable. All right. Don't worry about the rest. That is just extra information you don't need to worry yourself about. So let's continue this way. You see the table below shows the quantity of bananas in tons grown annually on a farm over the period 1986 to 1993. Right? So in 1986, 100 tons was grown. 1987, 200 tons. Okay, fair enough. Draw a line graph to represent the information and use the graph to answer the following questions. Okay, so to draw this line graph, right, if we come up with our scale, 1 centimeter represents 50 tons. So from here to here, if it has 1 centimeter, that'll be 50. Next centimeter, next 50 will give you 100. Next centimeter, 150, and so on. Okay, so that's how you would go on your y-axis, and that would be the quantity of bananas grown in tons. So in 1986, they said 100 tons were grown if you look at your chart, so we plot our first point, which would be this point right here. In 1987, 200 tons were grown, so that would be this point here. And so on until you get to your last point in 1993, they said 600 tons were grown, right? And of course, 600 comes across to get your point in 1993. And then you connect your dots together. Dot to dot, you connect it up. And that's why the graph looks like that, because it's just a matter of connecting up all the dots together. So that would have been your drawing, but you know, they wanted something solved. I'm just going to read the questions here and we're going to answer it. They say, during which period was there the smallest increase in the yield of bananas? So where did it go up? During what time it went up by the smallest amount, right? And you could see that during 1988 to 1989, right? Which is this period here, here to here, that period there. That was the smallest increase because there was no other period that went up only by 50 from 300 to 350. So that was the reason why that was the answer for part one, which is a period where there was the smallest increase in the yield from 1988 to 1989. The second question asks to find the period where there was the largest increase, where the largest increase would be the biggest rise. And you could see quite clearly that that's between 1991 to 1992, right? Which is this period here, right? There's no other period in the graph where it went from 200 to 500, which is an increase of 300 tons in that 1 year period. The next one was, the question was the yield of bananas, right? Or from the line graph, the yield of bananas was the lowest. When was it lowest? When was the yield the lowest, right? So let me see that again. In which year was the yield of bananas the lowest? It was not this one, right? You might go there because you will last in this area here. But the yield was the lowest here, right? That was the lowest point. And therefore, the yield was lowest in 1986. The next question and the final one was, during which period was there a decrease in the yield? Where did it go down? And that would have to be the period 1990 to 1991. 1990 to 1991, where you saw the graph going downwards like that. Okay, so that would be the period for part 4. Good, so that's line graph. Now, before we could go ahead further, we have to learn a few things, right? We have to learn about variables and a couple calculations, right? So what's a variable? Well, as stated previously, when we collect information which is to be used in statistics, we usually want to find out about a particular characteristics of a group of people or items. This characteristic is called a variable, and it usually changes from one member or group to another. Right? Now, variables could be divided into 2 types. They could be qualitative or they could be quantitative. And qualitative variables are those that describes the characteristic. For example, the height of a person could be short, average, or tall. Right? They're not putting any numbers, it's just a description. Whereas in a quantitative variable, which is the other type of variable, is one that has a numerical value. These variables are of 2 types. These quantitative variables could be of 2 types. They could be discrete or they could be continuous. Now, a discrete variable, a discrete quantitative variable will be one that could take certain definite values, right? It could only take, not could take, but only take certain definite values. And these definite values are usually whole numbers. Example is number of mangoes picked, right? You'll hardly pick a quarter of a mango, right? You'll pick whole mangoes. Or an even better one would be number of CDs sold. Right now, the CDs or DVDs, let's put DVDs sold, right? Because you can't sell 2.3 DVDs. You have to sell whole number among the DVDs, right? So discrete variables must take certain definite values. Whereas a continuous variable is one that could take any value within a given range. And you could obtain it by measurement. Okay? Example, when you're born, you have a certain height or length. And as you go from that height or length that you started with to your final height or length, well, let's say final height, right? You will find that your height could be anywhere within that range. At one point, you might be 1.1 foot. That's when you started, when you were born. And then as you move through at certain ages, you might be 3 feet. Then you might be 3.2 feet, 3.6 feet. And you remember you're continuously growing. So this is what we call a continuous variable. Or if you're weighing sugar, you could get 2.3 grams of sugar, right? And so on. So that's what you call continuous variables as opposed to discrete. We have a very important calculation known as, just one second. Right, we have a very important calculation. It's known as relative frequency, right? It's also called probability or experimental probability, and it could be stated as a fraction or percentage. So very often you will be asked to find the relative frequency or probability of something happening, of some event. And that is obtained by using this calculation, the frequency of the event over the total frequency. That's the main one we will use. Some people use this one, the desired outcome over the total possible outcomes. That's another nice one. But most of the time we use this calculation. And if they wanted as a percentage, then you multiply the answer by 100 to get it into a percentage. This is very important. So make sure and memorize these formulas, this one in particular. Right? From now on, you're going to see relative frequency or probability, which is the same thing, popping up very regularly. All right. So the first thing we're going to look at here is, to continue diagrams in statistics, is the histogram. And a histogram is very similar to a bar chart or column graph, except that there's no spacing in between the bars of the histogram. So if we read here, we see a histogram consists of a number of rectangular bars, which could be of different widths. But in our case, we don't ever use different widths. These bars are always drawn vertically and are joined side to side without leaving any space. Since there's now a regular scale along the horizontal axis, all of the diagrams before, we didn't have to put a scale on the horizontal axis. The scale only went on the vertical axis, all right? But in a histogram, you come up with a scale. Now, also, if you see no bar, it would tell you that the frequency of the observation is 0. All right, so let's go ahead with histograms now. In histograms, frequency is always plotted along the vertical axis, which is the y-axis, and the other observation or variable is always plotted along the horizontal axis. Another very important factor. All right, let's see some examples. Right, in this particular example, there's a frequency table. This is known as a frequency table, right? That shows the number of points gained by teams in a series of cricket matches. So 3 teams got no points. 2 teams got 1 point. No teams got 2 points. Or 2 points were not obtained by any teams. 3 points were obtained by 5 teams. And so on, right? There are certain questions to be answered. What's the first question? How many teams took part in the series? Well, how many teams would simply mean add up all these numbers here. Very simple. So you add it up. Now there's this symbol here, which is a Greek symbol. It's capital epsilon. And in statistics, you see this symbol being used very often. It means to add up or to sum up. So we add up all the frequencies, and that would tell us the total number of teams that took part, which was 31 teams. That's A. B, draw a histogram. C, if a team is chosen at random, calculate the probabilities. All right. Let's draw the histogram first. Okay. So you'd notice that in this histogram, we put in frequency on the y-axis. We put in points gained on the x-axis. And I kind of took the values here so we could see how we got these columns here. So when x, which is the points gained, is 0, the number of teams that gained 0 points was 3. Right? That was taken from this chart here. Right? I just did it over here. So frequency, which is the number of teams that gained any particular number of points, always goes on the y-axis. So no points, 3 teams. No points, 3 teams. 1 point, 2 teams. Right? 2 points, no team. So 2 points here, nobody there. So you see no bar there. Next one, 3 points, 5 teams. So 3 points here, 5 teams. That's why I go up to that height. Let's go down to the last one. 10 points, 1 team. 10 points here, only 1 team. That's why you went up to this height here. Right? Notice it's shaded here. When you're doing it, you can cross hatch it, right? Which is just simply parallel lines going along it. Just so you could see the bar easier, right? If you have time, you do that. If you don't, well, you know, you just move on. But it makes it easier to see it. And notice there's no spacing in between the bars. And notice that they are the same width. So this is known as a histogram. Okay. Now there are certain questions that they ask in part C. In this particular question, they ask a few things. The first one that they asked was, let's see. First one they asked was, if a team is chosen at random, right? If a team is chosen at random, calculate the probability that it gained less than 5 points, right? Calculate the probability that it gained less than 5 points. So if you look up here, to find the number of teams that gain less than 5 points, you'd have to go in this direction, right? Which means if 5 points is here, those that gain less than 5 points will be those that gain 4 points, 3, 2, 1, or 0 points. Now 6 people gain 4, 5 gain 3, no people gain 2 points, 2 people gain 1 point, and 3 gained 0 points, right? 3 teams gain 0 points. So in order to get the number of teams that gain less than 5 points, that means we have to add up these amount of teams here, which would be 3, 2, 0, 5, and 6. 3, 2, 0, 5, and 6. So we add these up and we get the number of teams, which is 16 teams. Now, the total number of teams that took part was 31. That's what we calculated. So if we want to get the probability that if you chose a team at random, right, that it gained less than 5 points, then that'll be 16 teams, right, gaining less than 5 points out of a total of 31. And remember, we learned that probability is the frequency of the event, which would be the 16 teams, over the total frequency, which is the total number of teams, 31. And this calculation here, which gives you this, would be the probability that you are looking for in part 1. In part 2, they said, what's the probability of choosing a team that gained exactly 5 points? So if you look, 5 points, the number of teams that gained exactly 5 points was 7. So the probability, which is the frequency of that event, 7 teams, out of the total frequency, 31 in all, would be this calculation here that give you 0.23. The next one was the probability that the team chosen would have gotten greater than 5 points. Well, let's look up here. Which teams got, how many teams got greater than 5 points? That would be those teams that got 6, 7, 8, 9, or 10 points. And these are the number of teams getting those points. So we'd have to add up these numbers to get the teams getting greater than 5 points. So if we add up that, we got 8 teams. 8 teams out of a total of 31 gives us the probability of 0.26. And then the last calculation here is, what's the probability that it gained at least 5 points? Well, at least 5 points means 5 or more. So that'll be 5.6, 7, 8, 9, or 10 points. And these are the numbers of teams gaining those points. So to get the teams that gain 5 or more points, you'd have to add up these numbers, which give us 15. So the probability would be 15 out of the total 31 teams, which is 0.48. So the calculations are fairly simple once you know the formula. It's what you're looking for out of the total is the probability that they want to calculate. Okay. The next thing we have to learn about, the next type of graph is known as a frequency polygon. And frequency polygons, let's see what they are. Another way of representing a frequency distribution is by drawing a line graph. So we know a frequency polygon is a type of line graph called a frequency polygon. They are most useful in comparing distributions, since it's a very easy way to draw 2 or more polygons on the same graph paper with clarity. All right, so this is just some academic information, but it's a type of line graph that we will learn how to do. So let's look at this here. The marks obtained by 50 students in a test where the maximum mark was 10 as follows. Right? So for a mark of 1, only 1 student got it. For a mark of 2, only 2 students got it. Let's go to a maximum mark of 10. There was only 1 child that got that mark. Draw a frequency polygon to represent the data and calculate those probabilities. Okay, so this is what the frequency polygon looks like. And basically, the frequency goes on the y-axis, and on the x-axis, you put the marks in this case. So for a mark of 1, the frequency was 1. For a mark of 1, the frequency was 1, right? So this point A is our first point. For a mark of 2, the frequency was 2. That's here. And you pull out all of those until you come to your last point, which is C, right? That's this point. For a mark of 10, the frequency was 1. So for a mark of 10, frequency here was 1. But you know something, if you look at this frequency polygon, you notice that we didn't start the frequency polygon at A, we actually started at B. And we didn't end it at C, we actually ended it at D, right? D should actually be a little further this point here. Now, so there's a little rule that you need to be aware of, and here's the rule above. This is the rule here. It says that always close off your graph at both ends at one interval. Now, this at one interval is really telling us how to close off your graph. So on this end here, which is your last point, right? On this graph here, if you look here at C, to close it off, which you must in all frequency polygons, you move one, you go one interval more. So the interval is the distance between these here, between 7 and 8, 8 and 9, 6 and 7, and so on. So how do you close it off? You just simply go one interval more than where this is. So you're going to go from 10 to 11, and your interval is going to be, you're going to end off at 11. So it's going to go from here to here. All right. So the interval is from here to here, and you extend this down to that point. Look on this side here now. The interval, you'd have to go back one, right? You have to go back one here, and that is where you're going to close it off at this position here, because the interval is 2 blocks, right? So in between each one of these is 2 blocks. So you're going to go back from your first point 2 blocks, right? And at that location, you're going to come back down. All right, so that's how you do your close off your graphs. In the next one, we're going to look at the calculations here. So the calculation for part B is, if a student is selected at random, calculate the probability that he scored no more than 5 marks. Let's look at that one. No more than 5 marks. So if you look up here, no more than 5 marks means he could score 5 marks or he could score less. So that means he could score 5, 4, 3, 2, or 1 mark, which means you'd have to add up all of these going backwards. So you'd have to add up 1, 2, 4, 7, 9 to find all the persons that satisfy no more than 5 marks, which would give you 23 students. And the total amount of students was 50. So the probability that they're looking for will be 23 out of 50 or 0.46, right? So that will be the answer for B part 1. And for B part 2, the probability that the students score at least 6 marks. At least 6 marks means 6 or more. So that would be 10, 8, 5, 3, and 1. That would be the number of students scoring at least 6 marks. So the total number of students scoring at least 6 marks would be, when you add up these numbers, so that'll be 27. So the probability you're looking for is 27 out of 50, according to this calculation, or 0.54. Now, sometimes you have group data. Everything we did so far was on group data. Sometimes you have frequency tables with group data. And that is because the data under consideration has such a large range of values, then it would be useful to collect these values into groups or classes, right? And the class interval is defined as the size or range of values of the group or class chosen. So let's have a look here. Consider the following frequency table for the weights of 100 students. So in this situation, we're going to learn about certain terms that you need to be aware of to be able to handle these types of questions. Right? So let's go here and we're going to learn about these terms. So I'm going to select 35 to 39, 40 to 44, 45 to 49, right? And write them down. I'm going to write these, what is known as the intervals, right, on this page here. So 35 to 39, 40 to 44, 45 to 49. So we could talk about different terms. The first term we want to talk about is the class rank. It is the order that the class appears in the frequency table. So if you notice, this was the first, this was the second, and this was the third sets of information. And therefore, that was the first class, second class, and third class. So the class rank tells you the order that it appears. The next thing we need to know is what is the class interval. It is the size or range of values of the group or class chosen. So 35 to 39 is the first interval, second interval, third interval, right? And the interval is 35 to 39 here, for example. Now the limit, class limit, which is the third point, are the extreme numbers in the class intervals. Sorry about that. Just excuse, I'm just pausing this for a second. Right, so continuing, the limits, right, are the extreme numbers in the class intervals. So if you look at the first class, right, let's look here. The 35 would be the lower class limit, and the 39 would be the upper class limit of this first interval. If we go to the second class, then the 40 is the lower class limit, and the 44 is the upper class limit. Third class, lower class limit, upper class limit, right? So you need to be aware of what limits are. These are very important because as we do the next set of statistics, you need to be aware and remember what all these things are. The next point is the class boundary. And this is the average of the upper and lower limits of two successive classes. Example, the upper boundary of the first class and the lower boundary of the second class. If we take the average of these two numbers, we're going to get that particular value. So let me illustrate that here a lot more clearly. If you look at this first class and this second class, the boundary will be that value that ends this one and begins this one. So how you calculate it is formally is you add 39 and 40 together and divide the answer by 2, and you'll get this separating value, which is known as the boundary, right? In a simple way, if you consider what is halfway between 39 and 40, it's quite easy to see it's 39.5, right? But the formal calculation is to add these two and divide the answer by 2. Now, this 39.5 could be called in two ways. It could be called the upper class boundary of the first class, and at the same time, it could be called the lower class boundary of the second class. So that's why, you know, it's something that you really need to understand. Let's go to this one here. Let's say, what is the boundary between the second class and the third class, right? And the answer is found by adding the 44 and the 45 together and dividing the answer by 2, which would give us 44.5. But from a common sense point of view, if you look at 44 and 45, then midway between the two, right, halfway, would be 44.5. That would be the exact center. So that would be the point which is known as the upper class boundary of the second class, because of course it's upper, it's higher than the 44. But at the same time, it's the lower class boundary of the third class because it's lower than the 45. But it actually just kind of separates the two classes and tells you where one class ends and the other one begins. Okay, so that's very important. It's called the boundaries. The next thing you need to be aware of is the midpoint, right, of the class limits or the class boundaries. And the midpoint, you have two ways you could calculate it. You could add up the intervals and divide by 2, or you could add up the boundaries and divide by 2. And that will give you the same answer, which would be known as the midpoint. So if I wanted to get the midpoint of this interval, I could add up 35 and 39 and divide by 2. I get 37, right? Or I could add up the boundaries and divide by 2, right? And I'm still going to get 37 if I add up 34.5 and 39.5 as shown here and divide by 2, I'll still get 37. So the midpoint, the class midpoint, could be found two ways: by finding the average of the boundaries or the average of the limits. Let's look at this one here. To get 42, I could say 40 plus 44 divided by 2 to give me 42, or I could use the boundaries, 39.5 plus 44.5 divided by 2, I'll get 42, right? But again, common sense and just observation would point to you that the midpoint is very easy. What is halfway between 40 and 44? If you just look at it, you would realize that 42 is halfway, the center value between the 40 and the 44. So you could do it by common sense. And after that, you can just say, okay, to get the midpoint, just add 2 to the lower class limit. So 2 and 40 is 42. 2 and 45 is 47. And so you could make up rather easy ways other than this formal calculation that they gave us here. The last thing we need to be aware of, which is known as the width of a class interval. It's called the class width or class size. And that is always equal as you go up like this, right? It is equal to the upper class boundary minus the lower class boundary. So if I wanted to get the class width here, I'll have to take 39.5 and take away 34.5 and I'll get 5. If I want to get the class width here, I'd have to take 44.5 and minus 39.5, I'd get 5 here. But there's an important note that they're pointing out to you. And what they're saying is, unlike the midpoints where we could get it by using the limits or the boundaries in these calculations, yeah, when you're doing the class width or class size, you cannot use the midpoint calculation. You cannot use the limits. You only can use the boundaries. Because let's say, for example, you wanted to use these limits to get the class width or class size, and I did the subtraction here. 39 take away 35 is not 5, it's 4. So I'm going to get a different value here if I try to get my class width by subtracting the limits. So that's a very important note that they pointed out to you here. You have to use the boundaries, which would give you 5, and you cannot use the limits, which would give you 4. But that is for number 6, so you can take a note on that one. All right. So we're coming to the final portions of this class here, this tutorial, where we're going to look at histograms for group data. Now remember, we did histograms for ungroup data just now. Now we're going to look at it for group data, right? And these could also be used to represent graphically frequency distributions with group data. Very importantly, in these cases, we're using group data. We will plot either the class boundaries or the class midpoints along the horizontal axis against corresponding frequencies. Let's see what that is about. So we have this frequency table here, and it shows that the weights of 100 students correct to the nearest kilogram are given in the frequency table below. So, for example, 5 students weighed 35 to 39 kilograms, 7 weighed 40 to 44, and so on. The first thing they wanted us to do is to draw a histogram to show this information. But how do we do it? Well, the important thing to know is that on the x-axis, you can either use these limits or you can use, not these limits, you can use boundaries, not limits at all, or midpoints. So let's see what that means. The boundaries for 35 and 39, that first interval here, the boundary on this side will be 39.5 and the boundary on this side will be 34.5. So when you're drawing this interval here, you would have to use those on your scale, right? So your scale would have 34.5, 39.5, 44.5 going up, which would be the boundaries that you would have gotten for, for this table. So the boundary between 39.5 and 40, 39 and 40 is 39.5. Between 44 and 45 is 44.5. So you're going to see these things here, right? These are the boundaries that you would have come up with. And that these boundaries would be for the interval 35 to 39. These two boundaries would be 40 to 44. These two boundaries would be the interval 45 to 49 and so on, right? So on your x-axis, this is what you would have, your scale would look like. And of course, the frequencies would go up here. So for the interval 35 to 39, right, if you look here, it was 5. So that means that since frequency always goes on the y-axis, the height here would be 5. For the next one, 40 to 44, the frequency is 7. 40 to 44, the frequency is 5, 6, 7. But remember, on your x-axis, you'll be using the boundaries, not the limits, right? Because you can't start at 39 and then jump to 40 because remember, this here has to represent something, which would be the boundary between these two, okay? So that's very important. Or if you didn't want to do this, you could have used the midpoints because the midpoint of 35 to 39 is 37. And you could use that midpoint to represent this interval. The heights would be the same as this option here. It's just that you'd be using the midpoints of the intervals along the x-axis. So 37 would be here, 42 would be in the middle, 47 here, 52, and so on. And that's how you come up with the positions of each of these, right? And then you use your frequencies that you would have had from your table here, right? To get your various heights. So this is how you would do histograms, either the boundaries on the x-axis or the midpoints, which would be in the middle of each of these bars, right? But there were some questions they wanted you to do. First one was, what is the relative frequency of the class 60 to 64? Now, you guys, relative frequency is the same thing as probability. Or they might even throw in a big term, experimental probability. But you have to know it's the same calculation that we were using all the time. What's the calculation again? Well, relative frequency and probability both carry this calculation, which is the frequency of the event you are interested in over the total frequency. Now, what is the event that they were interested in? Well, the event that they were interested in is this. What is the relative frequency of the class 60 to 64? Well, 60 to 64 has 17 persons in it. So the relative frequency, right, would use this 17 as the required frequency on top over the total frequency, which would be the total number of students, which they told us was 100, right? Let's see. The weight of 100. Also, if you add up this, you will get 100. So you know that the total frequency to get your relative frequency in this calculation would be the 100 figure. So it'll be 17 students out of 100 would be a relative frequency. And it would, if they had asked you the probability, you would also do this calculation. So the answer was 0.17. Right? The next question they asked here was, what percentage of students weighed between 55 kilograms and 64 kilograms? Well, 55 and 64 would be these two, 55 to 59 and 60 to 64. That would cover the range 55 to 64. So you'd have to add up these two amounts, which would give you 30 students in all, would cover that area, which is students weighing between 55 and 64. Now, they didn't want that amount alone. They wanted percentage. So percentage would be 13 plus 17, 30 students out of 100. That'll give it the fraction, but they wanted percentage, right? Let's go back and calculate and double check. What percentage of students weighed between 55 and 64? So we had to get the total number of students weighing between 55 and 64 divided by the total number of students and then multiply by 100 to convert it to a percentage. So it's very important to look at the actual question that they want to find out. Okay, and the last thing we're looking at for this evening would be frequency polygons for group data. We did the frequency polygon, which is a line graph, right, for on-group data. Now we have to look at it for group data. Frequency polygons can also be used to represent distributions with group data. The frequency polygon for group data is obtained by doing something specific. What is it? By plotting the midpoints, right? It's important, midpoints of the class intervals on the x-axis against the corresponding frequencies on the y-axis. And then we draw the straight lines as we did before. So let's remember, midpoints on the x, frequencies on the y. Frequencies is no problem. So if we take the information they have, which is in this example, draw the frequency polygon for the following distribution of exam marks obtained by 115 students. So you saw that 3 students got anywhere between 1 and 10 marks. 3 students got anywhere between 11 and 20 marks. So this is group data. They're grouping the marks. Now, if we have to draw a frequency polygon for group data, we already know that on the x-axis, we have to get the midpoints. So we're going to get the midpoints between 1 and 10. How you do that? You add up 1 and 10 and divide by 2. So that's 11 divided by 2, which will give us 5.5. So there's the midpoint here. What's the midpoint here? 11 plus 20 is 31. Divided by 2 gives us 15.5. 21 plus 30 is 51, divided by 2 gives us 25.5. 31 plus 40 is 71, divided by 2 gives us 35.5. But at this point, I am getting a little tired of adding and dividing by 2. So I'm going to look for a pattern. And the pattern that I see very nicely is either to add 4 to each one of these lower limits or simply go up by 10. because 10 plus 5.5 is 15.5. 10 plus 15.5 is 25.5. 10 plus 25.5 is 35.5. So I made that observation, and I could use that to help me to reduce the workload that I have. So I'll just continue adding tens. 45.5, 55.5, 65.5, 75.5, 85.5, 95.5. So without doing that adding and dividing by 2, I could just quickly ramp up and write down my answers just because I observed, right, which is important. Learn to observe patterns. And the pattern here was simply to add 10, going all the way up. Why did I do that? Well, the answer is that I have to use these numbers on my x-axis. So 5.5 would be linked to 3, right? 5.5 would be linked to 3. So that will be my first point. That will be 3 students earned between this mark, and I'm using 5.5 to represent it. So 5.5, 3 students. That'll be my first point. The next one was 15.5, 3 students. 15.5 here, 3 students. What's the next one? 25.5, 8 students. 25.5, 8 students. And you would plot all these points in that same one until you came down to this last point. What's the last point here? 95.5, 3 students. 95.5, 3 students. So that's here. So that will be our last point. But remember something. In frequency polygons, you must always close off your diagram. That's a very important thing we have to remember. So how do we close off? Well, whatever the interval is, in this case, between one mark and another, one graduation and another, there are 2 blocks. So from our first point, we needed to go back 2 blocks and bring our line back down to that point. So that's where we're going to close off the left-hand side. Let's go to this point here. This is our last point that we plotted based on the information given in the table. So we have to go forward to the right, 1 interval more. Remember, interval is 2 blocks. So from right here, we're going to go 2 blocks more, 1, 2. And that is where we're going to close it off by bringing the line down there. So we close off at this point D. Always remember to do that closing off. Also, something to note here, just a reminder, that we did this scale here to make it easy for us to plot the points based on the fact that we had to get these 0.5s. We chose that scale to help us. But there's a little variation here because from here to here is 2 blocks representing 5.5, but afterwards 2 blocks is representing 10 because the difference between 5.5 and 15.5 is 10 here, right? So these 2 blocks would be 10. The difference between 15.5 and 25.5 is 10. So these 2 blocks represent 10 as well. But between here and here, even though there are 2 blocks, it's not representing 10, it's representing 5.5. So there's a little difference in the scale. So just to show the examiner that we did this on purpose to allow us to get all these points plotted very quickly, we broke the line here with this little up and down, right? And that shows them that we purposely broke the scale there and that it would be different all the way through. So they wouldn't take off any marks for having a different scale at that point. We didn't have to calculate gradient or anything, so it didn't make a difference. It just meant that it made our life very much easier in terms of plotting. In this final one, right, we learned that very important point that, of course, for group data, we use midpoints in the x-axis. All right, so that will bring us to the end of this session here, right? I don't know if you guys are okay. I'm hoping that you guys are okay and able to close off at this point. Any questions?
No, sir.
All right, Cassie, nice to see you there and throughout the whole session. Bessie, first time I'm seeing you. Nice to see you here in the class. Celine, nice to see you. Journey, I know you're here regularly, so keep it up. All right, I'll be sending you guys multiple choice probably tomorrow to work on, and we'll correct it on either Wednesday or Tuesday. So stay tuned for that because you know we have to beef up on the multiple choice questions, and soon I will send out the paper 2, paper 3 questions for those who have to do that aspect of it. All right. So God bless, and I'll see you guys in the next class. Take care.
You too, sir.
All right. Thanks, Cassie. Bye, Celine. Jenny. Okay. Bye bye. All
I
right. Bye, Bessia. Take care.